eventually converge to a solution of the inclined plane problem based on some of the inputs that I gave to you, where I said A is the relative acceleration of the particle with respect to the inclined plane, which would be evidently along the plane, and capital A is the acceleration of the inclined plane itself because of an unbalanced n sine theta, which we saw earlier. Then the resultant of small a, relative acceleration with the acceleration of the observer, would give me the acceleration of the particle in the ground frame. Now, therefore, if I resolve capital A, that means I have to essentially find the resultant of small a and capital A so as to perceive the acceleration of small m in the ground frame. So I resolve capital A as a cos theta parallel to the plane and a sin theta perpendicular to the plane. Right? So essentially, if I add a cos theta, a sin theta, and small a, that will give me, this resultant will give me the acceleration of small m in the ground frame. Right? Therefore, in the ground frame, parallel to the plane, what's the acceleration parallel to the frame in the ground frame? A minus a cos theta. A minus a cos theta is the acceleration of small m in the ground frame. So this is all in the ground frame. Whereas a sin theta is the acceleration in perpendicular to the frame, perpendicular to the plane, as seen by a ground observer. So the ground observer sees a minus capital A cos theta parallel to the plane and capital A sin theta perpendicular to the plane on small m. That's now. So this is the effect of whatever is happening on small m. What is the cause? Okay. So what causes a sin theta on small m? All forces perpendicular to the plane will result in capital A sin theta. What are the forces perpendicular to the plane? Mg cos theta minus n. Mg cos theta minus n will cause a sin theta, right? So mg cos theta minus n will cause a sin theta, right? So that's equation 3. So equation 1 was like the inclined plane having an acceleration a, as we saw earlier, because of n sin theta. N sin theta is capital M into a, right? Now, parallel to the plane, what's the acceleration? A minus capital A cos theta. And what causes that? All forces parallel to the plane, that is mg sin theta. So mg sin theta causes a minus capital A cos theta. So mg sin theta causes small a minus capital A cos theta. This acceleration. That's equation 4, right? So what I'm going to do is, I'm going to use equation 1, which is this equation, and I'm going to use equation 3, which is this equation, and first solve for n. Solve for n. Right from this equation, as you can see, I can replace n by ma by sine theta. Capital Ma by sine theta, by the way. Capital Ma by sine theta into this equation. And first I'll solve for capital A, the acceleration of the inclined plane. See what it turns out to be. So this is like a mg cos theta minus n replaced by capital Ma by sine theta equals small ma sine theta, right? I transpose this on this side. I get mg cos theta equals a into, if I add these two, capital M plus small m sine square theta divided by sine theta, right? That's what happens. A then turns out to be mg cos theta sine theta, mg cos theta sine theta divided by capital M plus small m sine square theta. That's the acceleration of the inclined plane, mg cos theta sine theta by capital M plus small m sine square theta. Good. Now once I have capital A, can I not solve for small a? Can I not solve for small a? I can plug in capital A into this and solve for small a. Solve for small a. Resultant, the relative acceleration of small m in the inclined plane frame of reference. So let me go to equation 4. I cancel m, and then I have like a small a equal to g sine theta plus a cos theta. G sine theta plus a cos theta, capital A cos theta, right? Let me simplify this. Replace a by this. So when I do that, let's see what happens. Right here, A is g sine theta plus capital A cos theta. That means mg cos square theta sine theta. See, g cos, I'm saying A cos theta, this into cos theta, so mg cos square theta sine theta divided by capital M plus small m sine square theta, right? See what happens. From these two, I'm going to take g sine theta common. So if I took g sine theta common from these two, if I took like a g sine theta common from these two, then I end up getting 1 plus m cos square theta divided by capital M plus small m sine square theta is what I get, right? Let's see what this turns out to be. So if I add small m sine square theta plus small m cos square theta, that will give me m. So capital M plus small m in the numerator, capital M plus small m into g into sine theta divided by capital M plus small m sine square theta. So here we have, eventually, after a lot of deliberations, after a lot of detailed analysis and discussion, we have the acceleration small a with respect to the inclined plane available to us, and the acceleration of the inclined plane as well, right? Now all that I need to do is, if I vectorially add small a and capital A, I'm going to get the net acceleration in the inclined plane frame of reference. I'm going to get the net acceleration in the ground frame of reference. Yes or no, right? So this does seem like an interesting situation to deal with. Here what I did was the basic premise of adding the relative acceleration to the acceleration of the observer, which is the inclined plane, and then looking at forces on the particles small m. This time writing their net effect perpendicular to the plane and parallel to the plane. I could have looked upon their net effect in the vertical direction and horizontal direction as well, which is what I'm going to address in a short while. Thank you so much. Bye.